records on the cloud. Yes, okay. So today I will talk about container runtimes in Kubernetes context and show you guys the right path to choose your best container runtime for your Kubernetes clusters. First of all, I would thank the Kubernetes community for giving me this opportunity to share with you some knowledge about the lovely Kubernetes solution. My name is Fahed Dorgaa. I am a DevOps engineer and a cloud designer. Here you find my email, fahed.dorgaa@gmail.com, and my two profiles, LinkedIn and Twitter profiles. You are welcome in my profiles to discuss subjects about Kubernetes and container runtimes. So you are very welcome, guys. So during this presentation, I will start by defining the container runtime. So together, we'll try to find a simple and a generic definition for container runtime. The second part will be about container runtime interface and what is the difference between a container runtime and a container runtime interface. And the third part will be about the reasons to use container runtime interface. The fourth part will be about the best container runtime solution. And is it really, there is really a best solutions. And the last part will be about the integration of container network interface with the container runtime interface. Okay. So the first part, which is the famous question, what is container runtime interface? I hope that you like the picture. Personally, I found that it is a little bit funny. So let's check up what is saying this little boy. Not sure if this refers to Kubernetes container runtime, low-level container runtime, or movie container runtime. Yeah, guy, I know it's a little bit funny, but let's be more serious about the subject. So during all my containerization project, I heard a lot of times the word container runtime, and each time this word have a different meaning depending on the context. Today, through this presentation, we will try to find together the meaning or the simple and generic meaning of container runtime in Linux and exactly in Kubernetes context. So in the way to our definition of container runtime, I will compare two different approaches. As you see in the picture, guys, in the left side, we have virtual machines, and in the right, we have containers. So virtual machines are built on top of an infrastructure, which can be a virtual, like cloud infrastructure, or physical infrastructure. So on top of this infrastructure, we have an hypervisor, which is a tool that provision virtual machines. Like you see in the picture, in this example, we have 3 virtual machines. So on each virtual machines, we have a guest operating system. And on top of this operating system, we find libraries, binaries, application, etc., etc. But in the other side, we have containers. So the low level of containers is the same as virtual machines. We also have an infrastructure, which can be virtual or physical infrastructure, but here is the major difference. So on top of this infrastructure, we have an operating system and not an hypervisor. And this operating system will handle a container engine that will provision containers, which will contain binary, library, and application. So if we compare the two approach, guys, we find that the operating system in virtual machines is a guest operating system, but in containers is a host operating system. And that explains why containers are faster than virtual machines. And it's very easy to deploy containers than virtual machines. The word runtime is a bit ambiguous. Each project, company, or community has its own and usually context-specific understanding of the term container runtime. Basically, the runtime is defined by set of responsibilities. Like you see in the picture in the left side, we have a low-level runtime. The responsibilities of RunC are creating namespaces, starting and initializing processes. But guys, in the right, we have a high-level container runtime, like containerd, which is able to make image operation, for example, pull or push image, the sample operation of image management. So guys, to summarize the container runtime types, I can say that the high-level container runtime are built on top of a low-level container runtime, like Kata or RunC. Here we are talking about the low-level container runtime, which is RunC. RunC is based on Linux terminology like isolation or process isolation that we need to create containers. But don't worry, guys, I will explain those terminologies for those that may not be familiar with them. So first of all, we have the concept of namespace. But pay attention, I am not talking about a Kubernetes namespace. I am talking about a kernel namespace. So the namespace isolates resources from each other. The resources in the same namespace can see the same thing, but if they are not in the same namespace, they can't see the same thing. For example, we can take the example of the house, which is the system, and rooms are namespaces. Indeed, each child or each room, for example, give privacy to a child that can't see what is happening in the other room. Personally, I think that the concept of namespace is a pretty way to organize our system resources. So when talking about namespaces, there are three relevant terminology, which are PID. So the PID is the processes ID. Based on the previous definitions, we can find the same PID in different namespaces with the concept of isolation. And the second terminology, which is very important, is the network namespace, which makes the abstraction with the host network. So in each network namespace, we have a network interface that enable communication with the other network namespace, or even the host namespace, or where we host this special namespace. And the third terminology is the mount namespace. So the purpose of this terminology is to mount file system in containers without conflicting with the host file system. When we talk about the future of the concept or the concept of namespace, we have another important concept, which is Linux C groups. The target of the Linux C groups is resource limitation. So this Linux future attributes to each network namespace the amount of resources that the system can consume. Excuse me, I just will check something. Okay, it's good. So after these definitions of terminology and this path, I present you a simple and a generic definition of container runtime, which is a container runtime is a software that executes containers and manages containers images on node. So don't hesitate if you have questions about the definitions, guys, in the end of the presentation or even on the presentation. So the next part will be about container runtime interface and what is exactly the container runtime interface. Compared to the previous headline, like you see in this slide, I added the word interface. In fact, from a technical perspective, interface is a contract that enforces abstraction. I mean by abstraction, the guarantees to a client how a structure will behave. And I mean by abstraction, a really decoupled solution. The container runtime interface make abstraction between client and container runtime. We will see later the benefits of making this abstraction. But first of all, let's check what is container runtime interface. When I say abstraction, I mean an interface between client and the container runtime. So with container runtime interface, we can make a pluggable solution, which is very important today in microservice solutions. Indeed, in Kubernetes today, we can use a different container runtime with the help of the CRI, the container runtime interface. For example, we can use containerd, CRI-O, Docker, and many other container runtimes. For example, in the case of Kubernetes, the client of this interface is Kubelet. Indeed, with CRI, Kubelet can communicate with runtimes, for example, Kata or Franci, in order to create containers in the operating system layer. In fact, the runtime will create some stuff in the OS layer, like namespaces and C groups, terminologies discussed in the previous slide, which are the very important terminologies in the Linux and Kubernetes context. So guys, in the next parts of this presentation, I will discuss a different implementation of container runtime interface. Then I will try to compare them in order to define which container runtime can fit in Kubernetes better than the others. So here I am in the third part of our presentation, which is the reasons of using container runtime interface. So let's find out what are the reasons to use this container runtime interface. Today, there are many reasons to use CRI in Kubernetes. The most important reason is the abstraction between Kubernetes client, which is kubelet, and container runtime. So this container runtime, on the context of this container runtime, for example, developers can focus in developing their solutions without touching the Kubernetes code and architecture. Also, testing becomes easier because we have a microservice and a decoupled architecture. In addition, when using a CRI in Kubernetes, we can choose among several container solutions. And therefore, it is better to go to a solution which consume less memory and CPU, which is very important in resource consumptions. And the last point, using interface provides a clean API, more flexible for extensibility and embedding solution and project. So I use it to manipulate Docker or container in my several experiences as DevOps engineer. Over the year, the most popular runtime was Docker. I think we share the same information and the same experience. As you see in this picture, Docker is composed from many layers, which are networking, storage, and container runtime, which is in the middle, this layer in the middle of the picture. I am sure that you find that is logic to have this infrastructure and this architecture in Docker, but guys, Docker or Kubernetes doesn't need all of that. I am sure you are wondering how Kubernetes will work without networking and storage. Don't worry, guys. Kubernetes has its own networking solution via container network interface plugin like Weaveworks, and its own storage solution via storage classes, persistent volume, and persistent volume claims. So what would I really need in Kubernetes context? Let's make some suspense. Okay, it's enough. Let's go to the answer. So from Kubernetes overview, we only need the container runtimes, this portion of layers, as you see in the picture, guys. So this portion of layers, which is containerd, is the official solution of container runtime in the Docker solution. Containerd is composed from two main parts, which are container runtime, like runc in this example, and the snapshotter, where it will store the image and the impact layer of this image. I will explain later the containerd architectures in more details. So if I want to summarize the use of Docker in Kubernetes ecosystem, I will say that Docker is more than enough for Kubernetes. And also in Kubernetes ecosystem.
Sorry to interrupt you. Some people are waiting to get admitted to the session. Do you see anything where you have to click and allow people to come in?
Yes.
Hello.
Yes. Hello all. I'll try it because I didn't get the notification for this. It's a little bit strange. Okay, so invite. I don't see the notification for this. Okay. So I don't know, Ash, if you have the privileges to authorize people to go in session. They can join virtual. Yes. Oh, yes. Okay. Cool.
Okay, thanks.
Welcome. So, what I am saying. So, I said that there is another problem for not using Docker in Kubernetes ecosystem, which is the mismatch of release synchronization between Docker and Kubernetes, which always, or usually I would say, leads to bugs in many times. And finally, an extra memory and CPU use due to the extra layer with Docker. And guys, these constraints are very important today when talking about resource conceptions. So now I will talk about the best, this magic, the best container runtime solution. And we will try to find together, guys, if really there is a best container runtime solution or not. To be honest with you, there is not a best solution to fit in Kubernetes today, but there are many good solutions like Containerd. So I am very happy to be one of contributor on Containerd, and I think that Containerd is better than Docker in Kubernetes context. It's not the best one, but it's still a better solution in this context. So as of February 18, 2019, Containerd is officially a graduated project within the Cloud Native Computing Foundation. So Containerd is an OCI, which means Open Container Initiative, compliant core container runtime designed to be embedded in large systems. Also, as I said, compared by Docker, Containerd provides the minimum set of functionality to execute containers and manage images on node. Go to the next slide to understand this sound. So Containerd is a container runtime with an emphasis on simplicity and portability. It is available as a daemon for Linux and Windows, which can manage the complete container lifecycle of its host system. Excuse me. So I said that this solution can manage the complete container lifecycle of its host system. I mean by this the image transfer and storage, container execution and supervision, low-level storage and network attachment, and many other stuffs. So Containerd is a pluggable solution, which make it very powerful. Like you see in the picture, I will zoom a little bit in the picture, yes. So I have a message, yeah. Can you keep? I don't understand. Can you keep video off? My video? You mean my webcam? Okay. Take. Okay. Okay. So I said that this solution, the Containerd solution, is a pluggable solution, which make it very powerful. Like you see in the picture, multiple clients in this solution, like Kublet, we have CTR, we have Containerd client, we have Prometheus. There is many clients which can be pluggable to Containerd today. So this client can communicate with the gRCP API, which is an API provided by the Containerd daemon to manage multiple containers. But behind this API, we found a modular architecture, like it is designed in this picture. The use of modular architecture is very important when we evoke a pluggable solution and component-based solution. So among these components, we find the snapshotter, which is provides an API for allocating, snapshotting, and mounting abstracts. So the snapshotter, which is down in the left. Then we have the runtime manager, exactly the Containerd shim, which is an interface that could be implemented in order to create shim object. Indeed, each container has its own shim that acts as the direct parent of the container's processes. Guys, in Containerd, the daemon is a management API for multiple containers, whose lifecycle is very, very tied to one shim per container. I will deep dive in some flow of Containerd. Here we have a Containerd pull flow. So it's not very difficult, it's a simple flow. So it's a sequence diagram. As you see, we have this entity, the client will contact the registry to get a manifest, and then client will store this manifest in content store. Next, the client will get the layers that correspond to this manifest and store these layers in content store. And next, the Containerd daemon will impact this layer, they impact this layer and the descriptor. And after this step, all these layers are committed to snapshotter to make snapshot. And finally, we have an image which is created from this snapshot. This picture describes the integration of CRI plugin in Kubernetes ecosystem. This plugin is the implementation of Kubernetes Container Runtime interface. As you see on the picture, Containerd operates on the same node as the kubelet, and the CRI plugin handles all CRI, Container Runtime Interface, services, requests from the kubelet, and uses Containerd internal to manage containers and container images. So let's take the example of creation of one container pod to demonstrate the way the CRI is working. So the first step, Kubelet calls the CRI plugin via the CRI runtime. Excuse me. So I said Kubelet calls the CRI plugin via the CRI runtime service API in order to create a pod A. The second part, runtime service API, calls the CNI, this green box, to create a pod A network namespace and C groups. The third part, runtime service API, calls containerd client, as you see in this CRI plugin box, that will request containerd daemon to create a sandbox container in the pod A namespace with the containerd shim plugin. And the fourth part, Kubelet calls the image service API, the second service API, which is on top of runtime service API, in order to pull the desired image if it is not, of course, presented on the node. And the last part, Kubelet calls again the runtime service that will request containerd to create and start a container A in the pod namespace. So in this slide, guys, I made a comparison between containerd and Docker. As you see, in the first slide, we have the architecture of Docker, excuse me. So we have the same client, which is Kubelet. Kubelet will contact the Docker shim via the container runtime interface, and the Docker shim will request the Docker daemon, which will call the containerd daemon in order to provision containers in the OS layer. In the other side, the second line, we have the architecture of the CRI containerd, this containerd plugin. So the start point is always the same. We have Kubelet that contact CRI containerd that will request directly containerd daemon in order to provision containers. So as you see, in the CRI containerd architecture, we don't have the Docker daemon. So compared with the current Docker CRI implementation, CRI containerd eliminates an extra hop in the stack, making the stack more stable and efficient. And that's why CRI containerd is really faster than the Docker architecture, because we don't have this huge Docker daemon. Here I will present another open source solution that would be great alternative of Docker in Kubernetes context. We are talking about CRI-O. CRI-O is not graduated yet. I hope that it will be done as soon as possible because it is really a perfect solution. I tried it the last days. It's very perfect as a solution in container runtime for Kubernetes. So CRI-O implements the Kubelet Container Runtime Interface, which is the CRI, using the Open Container Initiative, the OCI. From a high-level overview, guys, an OCI implementation would download an OCI image, then impact that image into an OCI runtime file system bundle, which can be the CRI-O or containerd daemon. Then it would be run with an OCI runtime, for example, runc. So at a high level, the scope of CRI-O is restricted to support multiple images, including the existing Docker image format. Also, it would be restricted to container image management, like managing layers, overlay file system, and extra many and other many stuffs. And it can also be restricted to monitoring and logging operation. In addition, CRI-O can't sign and push images to various image storage. And like containerd, CRI-O can't build an OCI image. So comparing by Docker, CRI-O provides the minimum set of functionality to execute containers and manage containers on node. So in this slide, guys, I made a comparison between CRI containerd and CRI-O. It is a backed bunch. So this table has two lines, which are the compared solutions, which are the CRI-O and CRI-Containerd. And we have 10 columns. So in each column, we have a number of threads, from 1 thread to 10 threads. So each thread is equal to an operation. And in each operation, we have 3 steps, which are run container, stop container, and resume container. And these numbers are the results of the thread by solution. I mean the iteration. So, for example, if we take the example of CRI-O, in the example of 1 operation per second, we have 0.0.8 iteration. But in the case of CRI-Containerd, for 1 thread, I mean 1 operation per second, we have 0.14 iteration. If we take another example, in the case of 3 threads, I mean 3 operations per second. Remember, guys, the operation is 3 actions: start, stop, and resume. So in the case of CRI-O for 2 threads, we have 0.13 iteration. But in the case of CRI-Containerd, we have 0.25 iteration. So with those results, we can confirm that CRI-Containerd in Kubernetes context is faster even than CRI-O. So in this slide, we have a graph which is the result of the previous table. As you see in this graph, guys, we have the 3 lines. We have CRI-O, the yellow, CRI-Containerd, the red one, and Containerd, the blue one. As you see, the red line for CRI-Containerd is on top of CRI-O, and that is very normal because we said that CRI-Containerd is faster than CRI-O. But Containerd as an independent solution is very, very more faster than CRI-Containerd and CRI-O. So now we are in the 4th part of our presentation, which is the integration of container network interface with container runtime interface. So, Container Network Interface is also a cloud-native computing foundation project. It consists of specification and libraries for writing plugins to configure network interfaces in the Linux containers, along with a number of supported plugins. The CRI plugin uses Containerd to manage the full container lifecycle and all container images. CRI plugin also uses Container Network Interface to manage pod networking via Container Network Interface plugin and configuration. So, as you see in the picture, guys, Container Runtime provides the right configuration to the Container Network Interface plugin with this configuration file. So we have the green box, which is Container Runtime, which is the runtime, and the blue box, which is the network plugin. So Container Runtime invokes network plugin like bridge when container is added. Then the Container Runtime will create network namespaces with the help of this network plugin. So Container Network Interface can identify the network with I mean that Container Network Interface identify the network that the container must attach to. So now, guys, it's time of demo. In this demo, I will bring up a cluster with Kubadem. It will be a single machine cluster, And this cluster will use containerd as container runtime solution. But before this, I will check the message. What did you think about the fact? So Arash is asking question, what do you think about the fact that Docker and containerd are not supported anymore? And Unreal 8 plus families. It brings focus and avoids Docker issue. You just need one runtime. You can install an extra hop if you wish. What do you mean about it's about brings focus and avoids Docker issue? You just need one runtime. You can install an extra hop one if you wish at work. For example, we can give users with path. Yeah. So Arash, we need to give them sudo or to the yes. So Arash, I think that in the case of this operating system, I think that it's very important to support containerd because why? Because if we see today the architecture of containerd is a really pluggable solution, a solution that can be can interact very easy with other component in the system. So I hope that this operating system will support Docker and containerd. And really, I don't have very informations about the why containerd and Docker are not supported today. Are you saying something? Okay, so now I will. It's time for demo, guys. I will make a demo. So we bring up cluster with Kubadem. I said it will be a single cluster, and it will use containerd as a container runtime solution. So for this, I will exit from the. Okay. So that there is some. I have a small problem with the connection. Okay. For this presentation, guys, I made in the Kubernetes, yes. First of all, in the Kubernetes, our community repository. So we have a Kubernetes workshop. Under this repository, I created a folder which is CRI and Kubernetes meetup demo. So under this folder, you will find a descriptive and the steps that I will make to bring up cluster with Kubadem. So here you find all the steps from installing tools to download the containerd release table, from setting up CRI containerd, also the kubelet configuration to configure containerd runtime with containerd sockets, also how we will bring up the single machine Kubernetes cluster with Kubadem, configuring the client, enabling pod scheduling, and set up the cluster network. And under this folder, the demo script, I created an install tools shell that you will find all the functions and the instructions to execute all the steps of the presentation. So I will go to the readme. Yes. So the first step of the presentation is to create one machine, because we will make a demo in a single machine cluster. So we need one machine with these characteristics, 2 GB or more of RAM, 2 CPUs or more. Swap should be disabled, and this list of ports should be opened. So this demo will be on top of GCP. Okay, thank you, Arash. Thank you for sharing this. So in GCP, the first step, I will create my virtual machine. It will be one single cluster, so one virtual machine. The name will be CRI-O meetup. So guys, pay attention. It should be 2 or more CPU and 2 or more gigabytes of memory. So I will choose this one. N1 standard 2. So we have a 2 virtual CPU and 7.5 gigabytes of memory. So I will authorize HTTP and HTTPS traffic. It will be a Linux 9 disk for this machine, and I will choose Europe West 1 B, Europe West 1B as zone. Then I will create my machine. So depending of the network connection, maybe it will take some seconds. Yes. So now I have my machine, which is up and running on top of GCP infrastructure. So I will access to my machine via SSH. Okay. And the first step will be the install of tools. So in this step, I will install 3 tools: kubadem, kubelet, and kubectl. So for this, I will first of all install 3 libraries, which is libsecom2, apt transport HTTPS, and curl. Then I will add a key of a repository. Then I will add the repository. And finally, I will install kubelet, kubadem, and kubectl. Okay. So first of all, I will make a clone of our repository, but before that, I should install Git because it's really empty. So I get Git. So next step, I will clone the repository. Okay. And under this repository, I will go to the CRI and Kubernetes meetup demo script, and here I have the script with the function that I will execute to bring up our lovely cluster install tools. Okay. So as I said, the first step of this demo will be installing tools. So for this, I prepared this script with a list of functions. So this function will install for me the necessary tools. But before this, I should give the execution right for my script. tools, yes, and then I will call my script with the install tools function. Okay, he's installing kubelet, kubectl, and kubadem. Cool. Here we have the three binary are successfully installed. Okay. Is it okay? Is it good? Okay. So the second step will be about downloading the containerd release tarball. So in this demo, I will use the 1.3.0 release for containerd, and I will download it from Google Storage System, Google Compute Storage bucket of GCP. So for this, I have a little problem. I can't see comments because I made the zoom. Cat. What it will, it's install. Okay. So for doing this, the second function will be download containerd tarball. I think it will be more clear if I show you the script in GitHub. Yes, I think it is better. So the second function would be download containerd tarball, which will download from the bucket of Google Cloud Storage, the 1.3.0 tarball. So for this, I called this function. So we have the CRI containerd 1.3.0, which is saved. Cool. And the next part will be about verifying the checksum. So for this, I will get the checksum of my local tarball and the checksum of the remote tarball, and I will make a comparison between these two tarballs. So for this, I will, yes, so I call this function. So here we have containerd tarball, which is valid. Excuse me, Rafiq, if I zoom in the screen, I can't see the command line.
Say it again.
If I zoom,
yeah.
If I make a zoom, I can't see the command line. You know, the down part of my screen.
Oh, I think that. Yeah, I see that.
I don't know why, but
no, I think that you shouldn't like have the wide screen for the browser. Just put it like half of your screen, and it should be fine. Yeah.
Okay.
If you try right now, yeah. If you try right now, yeah.
Yeah. Okay, I see. Okay, I think it's better. Yeah. Okay.
No worries.
It's okay for you?
Yes, quite clear right now. Yeah.
Okay, good. So, so the execution, I will re-execute the verify checksum script to say if we have Oh, good. We have a container D tarball, which is valid tarball. You know, I have always the same problem. I can't see clearly the comments. I will try to zoom and dezoom the screen each time I execute a command. Okay, so the next step will be about the setup of container D. So for this, I will call a function which is setup container D. Before executing it, I will make a zoom. Okay, Vim. Okay, so the tarball is composed from some binaries, client binaries like CTR, CRI-CTR. So CTR is a client for testing the container D daemon. The CRI-CTL is for testing the CRI container D plugin of container D. We have this binary for container D daemon, container D stress binary, and also we have a container D shim for image or container API management. And we have container D shim for RANC version 1 and version 2. And here we have the container D dot service is the systemd configuration file that with this configuration file we will able to initialize the service and stop the service, make some operation of the service. So after installing the container D tarball, then I will create the container D kubelet configuration. So I will, yes, to execute the commands. And then I will make a zoom up. Okay, I think everything is good. I will show you the content of the output of the command in GitHub. So the output will be this, this configuration. So this configuration defines the configuration of kubelet of the surface, the configuration of kubelet service. So here you find the environment variables. Exactly, we define in these environment variables the container runtime endpoint, which will be the container D socket. So this is the endpoint that container D, that kubelet will communicate with. As we saw in the previous slide, container kubelet is the client of the CRI container D plugin. So in order to make this communication via the CRI, we should specify the container runtime endpoint, which is container D socket. Yeah, I should accept there is more persons. It's good. Okay, so if you want to check that we have the right configuration of container D, I will go to the container, to the kubelet services and check the content of container D configuration, and here we find the right environment variable with the right container runtime endpoint, which is container D socket. Okay, so the next step will be about bringing up the cluster with kubadem. So I will call this function So before making the command kubadem init that will initialize the cluster, I will activate some network configurations for the bridge, this network plugin, which is bridge. I will activate the IP tables, and I will activate the IPv4 forward in the case that we want to communicate with other network. We should activate the IPv4 forward on this machine. That in this case, this machine will be acting as a router for other network. It's very important to make these configurations, guys. Okay, cool. So we have our Kubernetes control plane, which is successfully initialized. So to start using our cluster, we need to run the following commands. So we need to create a .kube folder and copy the configuration file under this folder, and we should give the right privilege to the user in order to use this configuration. So these commands, guys, are for initializing and configuring the client of the Kubernetes API, which is kubectl. So for this, I prepared a function for doing this, which is setup kubectl configuration. I will call this function. Okay. I think everything is okay. We'll test later the kubectl. We will make some API requests. So the next step is to enable pod scheduling on master. So I should do this because we have a single node cluster. So we will create a pod on this node. For this, we would untaint the master node in order to have a node that is able to handle pod creation. So I enable pod scheduling. Yes, we have the node CRI-O meetup is untainted. And the last step will be the setup of network, which is very important. We should set up network in order to enable communication and network traffic between pods in the cluster. Setup networks. Yes, as you see, this command, this function, which apply a Kubernetes object. So I made a setup of a Weaveworks plugin. So it creates service account, cluster role, and cluster role binding, and daemon set to have this object and in all nodes in the cluster. So basically object for network plugin. So now I will try to check if our cluster is up and running. Yes, good. So for this, I made a kubectl get nodes. I have the name of the nodes, which is kube-cry meetup, which is ready. It's a master node, the age of the node, and we are on 1.16.2 Kubernetes version. So I will try to run an Nginx pod. Yes. And I will check if this pod. Okay, good. So this pod is up and running. We have a healthy cluster with a container runtime. Okay. There is more participants. Okay, guys, I'm done with this with the presentation. I hope that you like it. It was an overview about Kubernetes and the integration of the CRI container runtimes, which is CRI containerd or CRI-O or other container runtimes, and how you can choose the best solution and a solution that can be better than Docker in the Kubernetes cluster. So don't hesitate if you have questions. And thank you to be with us in this presentation. I will go to the chat channel. Computing.
So, Fahed, thank you very much. It was really great. Learned a lot myself. Hope others see. One question is coming up. How from Yayesh, how to run benchmark in this cluster? Which tool is used for that?
Yeah, there is a repository for benchmark. Yes, I forgot to make this to set this in the presentation, but I will write a comment in the meetup page or in our repository, or I will add in the presentation the link to the repository that describe and explain how to set the benchmark of Containerd.
Okay, thank you very much. One question from my side. So you mentioned during your presentation you had a look and played with CRI-O as well. On this implementation of the workshop which you have, did you try CRI-O as well?
You mean in comparing by Containerd?
Yeah, so what the implementation which you did with Containerd on Google now, did you tested that with CRI-O?
Really, yes, I made small tests of CRI-O, and as I mentioned in the presentation, I find that CRI-O is also a good solution in Kubernetes context. But I found that Containerd is more pluggable, is a solution that can be used today in Kubernetes and in other distributed systems. So, like Containerd, CRI-O is a good solution. Is very fast, but as you see in the bucket bench, CRI Containerd, this plugin of Containerd, stay the faster one today as a CRI container runtime for Kubernetes.
Okay, Fahed. You talked, first of all, thank you for the presentation. It was really helpful. You talked about limitations of these solutions like Containerd and CRI. What exactly are these limitations? Can I use a certified Kubernetes system with Containerd, for instance? Is there any kind of certification where Google says to use a container interface, it has to have this and this functions, and does Containerd fulfill this requirement, or are there any missing things that could bite me in the ass in the future?
Excuse me, I didn't hear very well. You can repeat your question? I have a problem with my connection.
Yeah, the question was, what exactly are the limitations of Containerd? You said that the basic set of functionality is guaranteed, but is there anything that could be missing in any project that I would use using Kubernetes? Is there any kind of certification suite for Kubernetes where the requirements have to be met to be used within Kubernetes?
Yes, of course, it will be, there is a limitation for Containerd today, like many other solutions. But I think comparing to other solutions like Docker and CRI-O, Containerd today can handle the traffic and the way that Kubernetes work very, very well. For example, from security perspective, I think that there is many tasks and work that we should do on Containerd in order to enforce the security in this solution.
Okay.
But I hope that you will have the opportunity to test Containerd. It is very simple as a solution. In the repository of Containerd, you will find an architecture, simple architecture of different components, and this project is created in. So this project is created, as I mentioned. It was graduated by the CNCF the last year, the February of 2019. So I find that it's really it's a good solution, but it's not very stable solution. We can add more functionality, and we can enforce the security in this solution.
Just I have one question here from the cloud provider for the managed Kubernetes services. Actually, do you know which one is widely adopted? Actually, for example, for container network interface, we got CRI-O, which is implemented by Azure, Google Cloud, and AWS. Is it the same case? Is there any solution from container runtime interface which is widely adopted by this cloud provider?
This is the power of Containerd. It's a pluggable solution. All of those solutions as a container network interface can be pluggable in Containerd because this system of API, this system of component of architecture, today we can create your own CNI plugin and integrate it in Containerd solution.
Okay.
Okay, but one question, let's say on AWS with EKS, the managed service of Amazon, they are still using Docker, right?
Mm-hmm.
And the network CNI implementation is something which is cloud provider specific. The question is, would it be possible to use Containerd with cloud providers as well? Do you know?
Yes, today in GKE, in Google Cloud Provider, the official solution is Containerd.
Ah, okay, good.
Yes, today. And the Containerd, I think, will be the official solution in Azure very soon. Okay, so nice. Yes, well, you're welcome. This solution become a very strong solution, and today I think more than 200 people contributing in the solution, and I think that it has a very good future.
So yeah, what we could do so in this case, that is like the same case as CRI-O, which is start like every cloud provider actually use CRI-O for container network enterprise. So it maybe will be like every cloud provider will be using Containerd as a base for the container runtime.
I'm not sure that every cloud provider will use it as a base of container runtime, but I think that there is effort today to try this solution by all the cloud provider. And personally, I hope that that those cloud provider try to test it and make a comparison with other solutions. So I hope that that it will be done. You know, I don't know, Rafik, if I give the right answer or no.
Yeah, it's quite clear. Thank you.
Yeah, you're welcome. But as I said, there is not really a best solution. There is a good solution for Kubernetes today. I saw in the CRI-O repository, the contributor in this solution may make many efforts to create a strong solution. There is a solution which is very, very fast. And depending on the use case, we can choose either Containerd or CRI-O, but not Docker, because Docker is composed today from other layers that Kubernetes doesn't need, like storage and networking.
We don't have any winners, so for the moment.
For the moment, no.
Okay.
For the moment, I don't think that Containerd will be the winner, but at least it's a good solution to use it today in Kubernetes context.
Yeah, so we had a short question which was answered by Walid regarding Docker support on Red Hat or Containerd. Red Hat is pushing CRI-O on Red Hat 8 versions, and they stop to support Docker. Maybe if one is wants to have Docker support, then they have to pay for that, I think. But and the whole tool chain on Red Hat is going to change. They are using Podman and Builder to build the images and so on. What do you think? How will the market react on such strategies from Red Hat?
Because maybe, guys, you can give an answer, but personally, I don't have a big idea, a real idea, what will be the future about this decision. I think that even I don't know what are the reasons that Red Hat doesn't support today Docker and Containerd, but I think it's not the best strategy to choose today, because Containerd and those solutions are really adopted by many orchestration system, distributed system today. But really, Arash, I don't have an answer direct answer for.
Yeah. I think I can help you with that. I think so. The reason that Red Hat went with CRI-O only is because in their OpenShift implementation they're using CRI-O, and so they've determined that they're going to pull out Docker and all of its functionality. It's still, you can still move it in or use it, but moving forward you're only going to be able to use, like someone else said, Podman, Builder, CRI-O, because these things give you better security footprint. And I think that was, that's the big problem that we see with the Docker. It has coming out of the gate, Docker gave you a lot of functionality but it gave it to you with a lot of, insecure ways. And so now they're really trying to figure out how do we dissect this huge thing called Docker that does everything and start to break those parts, break those things apart and make it a little bit more secure. So that's why, if you're using anything Red Hat related, they're going to push CRI-O for their CNI.
Okay, thank you for this clarification.
So I think though other Linux vendors like Canonical with Ubuntu or SUSE, whatever, they will support CRI-O as well, and maybe Podman on I think Podman is today supported on Ubuntu as well, and I'm not sure how Docker and the market around Docker and Docker's own Kubernetes implementation will continue to work on in the market. But yeah, CRI-O has its advantages. It's very secure, very fast, and let's see how the future will play.
Let's see the future, how it will play.
Okay, so there is another question from Palasundaram. How to contain system calls made from container D?
Arash, excuse me, I didn't understand the question. How
to contain system calls made from container D? To be honest, I don't get the question right as well.
Yes, I don't understand I don't understand the question. How
Sundara, would you explain?
Is made from to contain system calls. How to contain?
I think that the question means that how we make calls to like the kernel resources from the container D API, something like this.
Yes, the container D API. So the communication between the container D as a daemon and the system is there is of course the concept of system calls that able the communication between the container D, the low-level container D layers, which is the shim, the container D shim, that will make requests to the system, to the operating system, in order to provision the right resources. I mean by these C groups resources, or creating namespaces. And this isolation, it is made by this API, which is a pluggable API. Today we can implement our own solution in this shim, like for example, like Rancy, like Kata, gvisor. I saw that very soon it will be an integration between a provisor and containers. Will be an improviser-based container plugin that will be integrated in this shim. So from a generic overview, this communication will be made with these APIs. I hope
question answered, Palasundaram. Okay, thanks.
Welcome.
So, any other questions? Okay, if not, quiet. We will provide the link of your presentation on the meetup page.
Okay, thank you, Ash.
Okay, thank you. Okay.
Will you get the slide deck also for that?
Yes, the slides. Jeff?
I'm sorry, what's that?
You demand the slides, right?
If you, I was just going to say, like, I know you're doing the video, but can you provide the slides too?
Yes, of course. No problem.
Thank you.
You're welcome.
Okay, Fahed, thanks very much again for your great presentation, and to everybody for being on this Saturday at this time and joined us, and see you by one of our next meetups next week. Yeah, next week on Saturday.
Yes, of course. You're welcome, guys, and see you in the next meetups.
Thank you very much. Have a nice day.
You too. Thank you.
Thank you. Bye.
Bye.
Bye, everybody.